today's lesson is all about vectors. So a vector has length and direction. The length is called the magnitude and equals the distance between the initial starting point and the terminal ending point. Vectors are often used in physics to represent things with magnitude and direction, such as force and velocity. So we're going to do a couple things with vectors, but the first thing is talking about the magnitude. And since the magnitude is the distance, we're going to need the distance formula, which we've already learned. It is the distance between 2 points, x1, y1, and x2, y2 is given by our distance formula. D equals the square root of x2 minus x1 in parentheses squared plus y2 minus y1 squared. So that's the fastest way to get the distance if you know the coordinates of the 2 points for the initial starting point and the terminal ending point. But if we have a graph, you can also just look at it and know that this is going to be your horizontal distance and this is going to be your vertical distance. So for finding magnitude examples, we have this first one, which is easy. If it is just a vertical or horizontal line, you can just count how many units from our start of this vector to the end of this vector. And this one, it is 7 units, so the magnitude is 7. And number 2, since it's diagonal, we have to use our distance formula, but we do have the graph. So we can just know that our horizontal distance here is 2. Our vertical distance is 4. And then our distance formula is the square root of 2 squared plus 4 squared. Now, if we do that math inside our square root, 2 squared is 4, and 4 squared is 16. So 4 plus 16 becomes the square root of 20. Since the square root of 20 gives us a decimal, the way we have to type this in on IXL is as a simplified radical. So we need to simplify this. If we think back to our perfect squares, we think of the numbers like 2 squared, which is 4, 3 squared, which is 9, 4 squared is 16, 5 squared, which is 25, and we could keep going with that list, but what we're looking to do is take out any of those values if they are a factor of this number. So do any of these numbers go evenly into 20? And our one that does is 4. So we break this up into the square root of 4. And 4 times what is 20? That would be 5. So we just changed the square root of 20 to the square root of 4 times the square root of 5. And we know the square root of 4 is 2. So the simplified radical answer is 2 square root 5. Okay, it gets easier from here. So the component form of a vector, we're just saying what makes up this vector in terms of our horizontal and our vertical distance. So from here to here, we go left 6 in our x direction. So we would write -6. And our vertical direction from here to here, we go up 7. So we would just write -6, 7. Our second example, in our x direction, we go to the right 5. So we need to put 5. And then we just go up 1, so it'll be 5, 1. And that's the component form to describe these vectors. Okay, if we are adding vectors, essentially what's going on is we have one vector followed by another one, and we want to see where the ending point is. So we want to describe where those two vectors combined end up. So using our component form we just talked about, if we look at this one, it goes from here to here, that's vector B, then from here to here, that's vector C. So our ending vector, or where they end together, is right here. So we want to describe that in component form, which means we go right 2 and down 8. So we need to put 2, comma, negative 8. Then we don't have the vectors on this one, so we could draw them. We have vector B equals negative 2, negative 8, and vector C equals negative 6, 9. So if we graph both of those, we could see this ending vector like we did, but I'm actually going to do something different. If we just have the vectors in component form, we just need to add the similar components. So since negative 2 and negative 6 are our x components, we do negative 2 plus negative 6, which is negative 8. That's our x part of the component form. And then we have negative 8 plus 9, which is 1. And so together, in component form, this vector is negative 8, comma, 1. So now we graph that. We just need to start at the origin, as it says, and we need to go left 8, down 1. That is our component form of the vector. Okay, and then the last one, we don't have to do the graph. So just like we did before, we have 8, negative 9, and negative 6, negative 6 as our vectors y and z. If we find the sum, we just add those components. So 8 plus negative 6 is 2. And then adding our y components, we have negative 9 plus negative 6, which is negative 15, and that's our answer. Okay, the last thing is multiplying vectors by a scalar, which is also pretty easy. We have the component form of the vector, and so this is just saying we need 5 times that vector. So we multiply each component by 5. 5 times 6 is 30. And negative 7 times 5 is negative 35. If we want to graph a vector that's multiplied by a scalar, this time we have vector w, and we're supposed to graph 3w, which means we just need this vector at 3 times the length. So if we go from here to here on this vector, we are going right 5 and up 5. So we need to go right 5 and up 5. And that would be twice the size, and then we go right 5 and up 5 again. There's 3 times the size. If we connect those points, that creates our vector 3w. And the last thing, graphing negative 2v with the initial point of v. So what we can do on this one is write out the component form of this vector. If we start here and end here, it is right 5, up 6, so 5, comma 6. If we are multiplying everything by negative 2, then 5 times negative 2 is negative 10. And 6 times negative 2 is negative 12. So it says it has the same initial point, so we will start there. And then we're just going left 10 and down 12. So that is our graph of negative 2b. Okay, so that's it for our examples. Each page should help you with one section or one IXL that you need to complete, and those are due on Friday. So if you need help, I'll be there to help you later this week, but do as much as you can today.